Hello and welcome to the fifth and final video of the M3 chapter Dynamics. Exam question on the screen to review horizontal simple harmonic motion. A and B are 2 points on a smooth horizontal floor where AB is 5. A particle P has mass 0.5 kilograms, one end of a light elastic spring of natural length 2 meters and lambda 16 is attached to P and the other end is attached at A. The ends of another light elastic spring of natural length 1 and modulus of elasticity 12 are attached to P and B, as shown in the diagram. So over here we've got lambda is equal to 16 and L is equal to 2, and over here lambda is equal to 12 and L is equal to 1. We can see straight away that they are stretched already because 5 meters does not equal 2 plus 1. So we've got 2 meters of extension in here. And part A is asking us to find those extensions when the particle is at rest in equilibrium. So we've got T1 here, T2 here. So in this state, both of them must be extended. And the key point that connects those two extensions is that x1 plus x2 must equal the remaining length. We've got 5 there, 1 here, 2 here. So the extensions together must account for 2 meters. If it's in equilibrium, we also know that T1 equals T2. So for part A, we've got T1 equals T2. Lambda on T1 is 16 times x over L is equal to lambda for T2 times the extension for T2, which I'm going to call 2 minus x, divided by 1. That gives us 8x here, 24 minus 12x, 20x, 24, therefore x is equal to 1.2. I want both extensions, so let's say x1 is equal to 1.2, therefore x2 is equal to 0.8, where x1 is here and x2 is here. Part B. Initially, P is at rest in equilibrium. It is then set in motion and starts to move towards B. In the subsequent motion, P does not reach A or B, so it's moving towards B, but it doesn't get all the way there, and then it comes back. Show that P oscillates with simple harmonic motion about the equilibrium position. So we're being told that this point here is O, the center of oscillation, and we need to prove we've got simple harmonic motion. To prove that, we're looking to find our old equation x double dot is equal to minus omega squared x. So if we consider it when it is, say, here, then the extra little bit here is x. But not the x that I've used here. Maybe I should have called that E to avoid confusion. This then is not the extension of the springs, this is the displacement from the center of oscillation. So when the particle is here, from A, that is the natural length of A, 2, plus the extension we found in part A, 1.2, plus x, the displacement away from O. So the tension T1 in part B is equal to lambda times what we normally call x, I'll call E in this question, and that is 1.2, the extension we found in A to get up to the equilibrium point, plus x, the displacement from the equilibrium point, divided by the natural length L. T2 is very similar. We've got lambda for T2 times by extension, which is 0.8, the extension it gets just to get from its natural length up to O, minus x, the displacement from O, divided by the natural length. Now we can put these two together in the equation F equals NA, which I'll write as x double dot for A. And F is going to be T2 minus T1. Putting those in with lambda and L, we have 12 times 0.8 minus x over 1 minus 16 times 1.2 plus x over 2 is equal to the mass 0.5 times x double dot. That's 9.6 minus 12x minus 9.6 minus 8x is equal to 0.5x double dot. They cancel, and we get minus 20x divided by the 0.5 minus 40x is equal to x double dot, and that is of the form x double dot is equal to minus omega squared x, with omega equals 2 root 10, and therefore we do have a simple harmonic motion. Part C, given that the initial speed of p is root 10, remember it's being displaced from O initially, so this is the maximum speed when x is equal to 0. Find the proportion of time in each complete oscillation for which p stays within 0.25 meters of the equilibrium position. So we've got a few parts to this. We need to find how long does it take for one complete oscillation, because we need to state this as a proportion of that time. So for one complete oscillation, how long does it take? We can do that because we have omega. Then we need to find the time it takes to get to 0.25 meters, and to do that I'm probably going to need A, the amplitude. To find the amplitude I'm going to use the maximum speed in our speed equation. So that's my general approach. I'm going to need a bit more space here. So given that the initial speed of p is root 10, starting with this, with the equation v squared equals omega squared a squared minus x squared, we're told at x equals 0, v is equal to root 10. We also know that omega is equal to 2 root 10. From part A, putting these in, we get 10 is equal to 40 a squared minus 0. 1 over 4 for a squared, therefore a is equal to 1/2 of a meter. So it goes from half a meter over here to half a meter over here, and that's the full oscillation. What we want to know is when it gets to 1/4 of a meter. So now using x is equal to a sine omega t, when x is 1/4, we know a is 1/2, sine, we know omega is 2 root 10. How long does it take for the particle to go from the centre, which is why I've used sine and not cosine, from the centre to 1/4 of a meter. So t is equal to 1 over 2 root 10 times the inverse sine of 1/2. The inverse sine of 1/2 is pi by 6. So if I write that in exact form, we get pi root 10 over 120, which is equal to 0.0827 dot dot dot. And that is just the time it takes to get from O to 1/4 of a meter. But in a full oscillation it does that 4 times. Once on the way out here, then on the way back here, then again on this side, and again on the way back here. So we want 4 lots of this. So 4t is equal to pi root 10 over 30. Now we need to know the full period. Capital T is 2 pi over omega, and omega is 2 root 10, so if I simplify that we get pi root 10 over 10. The proportion then is this divided by this. We can see that we've got pi root 10 there, pi root 10 there, and then we're going to have 1 over 30 divided by 1 over 10, which is 1/3. So 4t over t, 1/3, and that is the final answer, the proportion of time p stays within 0.25 meters of the equilibrium position. In this video we're going to be doing very similar things, but instead of doing them horizontally, we're going to look at vertical oscillation problems. When solving a problem that involves a spring or string hanging vertically, we must remember the weight of the attached particle as part of the resultant force in our F equals ma equation. This has an effect on both the spring and the string situations. For springs, the weight of the particle means that the centre of oscillation for the spring will not be at its natural length, but at the equilibrium point, where t is equal to mg. For strings, the weight of the particle means the string will not necessarily become slack. In the horizontal motion, as it went from one side to the other side, there was always going to be a time of slack in the middle, where the particle was moving with constant speed. But for hanging vertically, the string will not necessarily become slack because it doesn't go on the other side of the fixed point. For example, if you've got a point here, and the string is hanging down and it's stretched down, and there's some upwards movement as it begins oscillating, If that movement only comes up as far as this, with the string still extended, and then it starts moving down again, there's no point of slack. It just goes up and down here and is extended the full time, so it's always going to be taut. However, it could become slack if instead of moving down at that point, it continues up past that point to the point where the distance between the particle and the fixed point is less than its natural length. The string does become slack there, and if that happens, it won't be moving with constant speed, it will be moving freely under gravity for this part of the motion as it comes up and then back down until the string becomes taut again, then it will go back to simple harmonic motion. So it does not necessarily become slack depending on the situation, but it might become slack, and if it does, it won't move with constant speed like it would horizontally, it moves freely under gravity. Some examples, and then I'll finish with an exam question. A particle P of mass 1.2 kilograms is attached to one end of a light elastic spring of modulus of elasticity 60 newtons and natural length 60 centimeters. Okay, immediately change that into meters. So lambda is 60, that's fine, but L is 0.6 meters. Mass, we also know, is 1.2. The other end of the spring is attached to a fixed point A on a ceiling. So it's fixed up here and is hanging down with the particle on the end here. The particle hangs in equilibrium at the point B, so this is A, this is B, and we need to find the extension in the spring. So for part A, we're doing work from the previous chapter, we haven't got simple harmonic motion just yet. In this situation, we know that there's mg here, and there's tension in the spring. If it's in equilibrium, which we're told it is, F equals ma is 0, the resultant force T minus mg equals 0, so T must equal mg. But we also know that the tension in the spring is equal to lambda x over L, and I'll try and remember to use E for the extension, so that I can use x for the displacement from the centre of oscillation later in the question. So we've got lambda is 60, extension 0.6 for the natural length, and mg, and we know m, so let me put that in 1.2 times 9.8, which gives us an answer of E equals 0.1176. So the extension there is 11.76 centimeters. But when we continue to use it in the equations, we should still be using meters. And I guess because I've used 9.8 for G, I should round that to 12 centimeters to two significant figures. Part B. The particle is now raised vertically a distance of 15 centimeters and released from rest. Prove that P will move with simple harmonic motion. Okay, although it says raised vertically, I'm actually going to show it below the point of oscillation, just because there will be a slight compression here, because this distance is greater than the extension we found, and I don't want that to confuse me. So we're going to have the natural length here. Then to get to the centre of oscillation, which I'll put as O, but it's already called B, and that was 11.76 centimeters, so 0.1176 meters. And now we've got x, which is going to be a displacement from O. So my particle is here. It still has the weight acting downwards and the tension acting upwards. But the tension now, lambda E over L, is lambda times 0.1176 plus x over L. So our F equals ma equation becomes mg minus lambda, which we know is 60, 0.1176 plus x over L, which we know is 0.6, is equal to mass times x double dot. Now it's worth noting here, if I go back a second, that this 11.76 centimeters here came from this equation, which was mg times by L divided by lambda. So if I write it like that, E is equal to mg L over lambda, and I leave it like that rather than putting in the numbers, then we can see over here that this bit here, mg L over lambda, when we expand this and multiply it by lambda and divided by L, we're just going to get mg left. And the mg minus mg, as we expand this bracket, the first term here, that will simply cancel out. And for simple harmonic motion, that will happen pretty much every time, because otherwise you would end up with a constant, and the constant does not fit into our simple harmonic motion equation. So it shouldn't be a surprise that when I put the numbers in, I get 1.76 minus 1.76 minus 100x is equal to 1.2x double dot. This number here, in this situation will always be the same, because this number has come from mg L over lambda, and you're multiplying by lambda and dividing by L. So here we get minus 250 over 3x is equal to x double dot, which is of the form minus omega squared x is equal to x double dot, with omega is equal to the root of 250 over 3. Therefore, yes, it is simple harmonic motion. And then we still have 3 questions to answer, the first of which is find the period and amplitude of the motion. Now the amplitude is quite straightforward because we have it here. If it's raised this distance and released from rest, then this is the amplitude. A is equal to 0.15 meters. The period, t, is 2 pi over omega, and we know omega is the square root of 250 over 3, which gives us pi root 30 over 25, which in decimal form is 0.688 seconds to 3 significant figures. Part D, find the speed of P as it passes through B. Now remember, B is the center of oscillation, the equilibrium point. So as it passes through B here, it's going at its maximum speed. So this is similar to saying find V when x is equal to 0, using the equation v squared is equal to omega squared a squared minus x squared. So that collapses to v equals omega a, and we know omega is the root of 250 over 3, and a is equal to 0.15. So that's the root of 250 over 3 times 0.15, which gives us v equals root 30 over 4, or 1.37 meters per second to 3 significant figures. Part E, find the speed of P at the instant when the spring has returned to its natural length. Now the natural length we know is 0.6, so that's down to here. And we know from the center of oscillation this distance here is 0.1176, and that is going to be our x value for this part of the question. The speed then, using the same equation, omega squared a squared minus x squared, becomes 250 over 3 times a squared, which is 9 over 400, minus x squared, and that gives me the answer 0.722 dot dot dot, square rooting that 0.850 meters per second to 3 significant figures. Example number 2. Particle of mass 0.2 kilograms is attached to one end of a light elastic string of natural length 0.6 meters and modulus of elasticity 8. The other end of the string is fixed to a point A on the ceiling. When the particle is hanging in equilibrium, the length of the string is L. Calculate the value of L. Similar to the previous example, this is just getting us to get the equilibrium point where mg is equal to the tension. We have lambda is equal to 8, L is equal to 0.6, m is equal to 0.2. So T is equal to lambda E over L gives us mg is equal to 8 E over 0.6, and with n as 0.2 and g is 9.8, that gives us an answer of 0.147 exactly. But that's not quite the end of it, because the value of L is the length of the string in equilibrium position. So capital L is equal to the natural length plus the extension, which gives us an answer of 0.747 meters. And although I've used g as 9.8, I think because there are no other decimal places on this answer, I might leave it like that because we're probably going to have to use this in a later question. So let's put that here and move on to part B. The particle is held at A, now A, remember, was the point on the ceiling, and released from rest. It first comes to instantaneous rest when the length of the string is k. Use energy considerations to calculate the value of k. So it's starting here, and it's going to finish, say, down here somewhere. And the total length of that is k. But we need to use energy considerations. So before we start, we have GPE is equal to 0, if I call A my 0 level for height. EPE equals 0 because at that point the string is slack, and the kinetic energy is 0 because it's released from rest. After the motion, at instantaneous rest at the bottom, the kinetic energy is still 0 because it's gone to rest again. EPE is equal to lambda E squared over 2L, using E as extension again, and GPE is equal to mass times acceleration due to gravity times h, and in this case I'm going to call that negative h because we've got 0 up here. It's a closed system, by which I mean no energy has been lost to friction or anything like that, so the total must remain the same. It's obviously 0 here, it must also be 0 here, so this plus this equals 0, so we get lambda e squared over 2l minus mgh must equal 0. We know lambda is 8, the extension is the thing we're trying to find. 2 times the natural length must equal the mass, 0.2, times 9.8, times the height. Now the height is k, because this length we're told is k meters. But I'm going to write it in terms of the thing we don't know in the equation, e, and that then is the natural length plus e. That gives me 20 over 3e squared, and although I took that term on the other side, I'm going to bring it right back again. So we've got minus 147 over 125 from the first part of the bracket, minus 49 over 25e for the second part of that bracket. This then is a quadratic equation in e, and in the exam you should show your process. So let's say minus b plus or minus the square root of b squared minus 4ac all over 2a, and that will give me 0.591 dot 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 or minus 0.297 dot dot dot. And because this is a string being extended, we can discard that one. So e is 0.591 dot dot dot, but k, which is what we really want, is the natural length plus the extension. So k is equal to 1.191 dot 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 1.19 meters to 3 significant figures. Part C follows on from that. Show that while the string is taut, P is moving with simple harmonic motion. This is fairly similar to the previous example. We're going to have our equilibrium point here, call that O, then this is capital L to there, which is the natural length plus the original extension, and then we're going to add on x, our variable. So the tension in the string is equal to lambda times the extension, the total extension, 0.147 plus the displacement from O divided by the natural length L. So in our equation F equals ma, we've got mg minus t is equal to mx double dot, and that gives 0.2 times 9.8 minus lambda 8 times 0.147 plus x over the natural length 0.6 is equal to 0.2 x double dot. And again, we should not be surprised that these two numbers are the same. We get 49 over 25 minus 49 over 25 minus 40x over 3 is equal to 0.2 x double dot, because this term has come from something that cancels with lambda and L to make mg. So again, shouldn't be surprised that they cancel. Rearranging this, we get x double dot is equal to minus 200 over 3 x, which is of the form minus omega squared x, with omega is equal to 10 root 6 over 3. Therefore we have simple harmonic motion. Part D. The string becomes slack again for the first time t seconds after p was released from A. Calculate the value of t. So let's consider the motion here for a second first. It starts at A at rest, falls freely under gravity while the string is slack, hits the natural length, let's say that's here, then it extends, but now it's under simple harmonic motion, not moving freely under gravity. It goes through the center of oscillation, out the other side, slows down, instantaneous rest at K, comes back through the center to this point, and this is where the string becomes slack again. And we're asking for the time after released from A. So it's all of this motion freely under gravity, and then from here, simple harmonic motion all the way back to here. So let's recognize here that this is not a full oscillation, because this part here is not a full amplitude of the motion, like this. The full amplitude of the motion is from O down to here at K. Go back for a second. K was 1.191 minus the distance to the equilibrium point gives us our value for A. So this is the amplitude, and the small distance from the natural length, 0.6, to L is only 0.147. So it's definitely not a full measure of the amplitude. So we can't just take one full period here, because it's not. So what we're going to need to do here is to calculate the time it takes to fall freely under gravity to here. Then from this distance, the time it takes to oscillate back to this distance, which from the center point O is 0.147. So that will be our x value when we try to calculate the time during the simple harmonic motion. First I'm going to do the freely under gravity part. So as we fall from A, we're using S is equal to the natural length of the spring, 0.6. A is equal to 9.8. Starting speed is 0, and we need the time, so we're using S equals ut plus a half at squared, where ut becomes 0, 0.6 is equal to 4.9 t squared, and that gives me root 6 over 7, and I'll leave it in exact form for now. So that's the motion just from A down to the natural length. Now for the simple harmonic motion, and I don't want to measure from this point because that would give me an awkward alpha, so I'm going to measure from here. How long does it take to go from here to here? And how long does it take to go from here to here? So I'm going to measure everything, including time, from here. How long does it take to go from here, down and back up? That's half of a full oscillation. So I could use capital T, get the period is 2 pi over omega, where omega was 10 root 6 over 3. That gives me pi root 6 over 10. But for this motion, from here down to here and back, I only want half of that. So half of t is pi root 6 over 20. Now I still need this little motion here, from here down to here, and then after it's done this, back up to here. So I want 2 lots of the time it takes to go from here to here, when x is equal to 0.147. So using x is equal to a sine omega t, we're using 0.147 is equal to 0.444 sine of 10 root 6 over 3 t. And that gives me the decimal answer 0.0413 dot dot dot. And I want 2 of those, 0.0826 dot dot dot. So my final answer, I've just realised I've used t down here when they've used t to mean something else here. Let's just call that t1. So our final answer, t, is equal to the time it takes to fall under gravity, plus this little time here, which is one of these, plus half of the full oscillation, which is this, plus another one of these little times here. So that's half of t1, which is pi root 6 over 20, plus 2 lots of little t, 0.0826 dot dot dot. And all of that together gives me 0.817 seconds to 3 significant figures. That was quite a big question. Let's finish with one exam question. A light elastic string of natural length L has one end attached to a fixed point A. A particle P of mass m is attached to the typo there, to the other end of the string and hangs in equilibrium at point O, where AO equals 5/4 L. Find the modulus of elasticity in the string. So we have our string, and it's down here, it's hanging with a particle on the end, mass m, there's tension in the string, and the natural length is L, but A to O is 5/4 L, so our little extension here is 1/4 of L. So we're using E is equal to 1/4 L, and we know that in this situation T is equal to mg, and also equal to lambda E over L. Lambda is the thing we want, so we've got mg is equal to lambda 1/4 L over L, the L's cancel, quarter comes over the other side, and we find that lambda is equal to 4 mg. That's part A. The particle P is then pulled down and released from rest. So now it's a little bit further down. It's going to be released from rest. At time t, the length of the string is 5L/4 plus x, so it's telling us something that we would naturally be doing anyway. We've got the natural length here, L, plus the quarter to get to O, plus the displacement from O, x. So this bit here is x. Prove that while the string is taut, this is true. And we can see that this is x double dot, x here, minus here, constant here. So this is a simple harmonic motion equation. At this point, we've got t is equal to lambda E over L, where lambda we know is 4 mg. E is now 1/4 L plus x, and L is still just L. So that gives us mg plus 4 mgx over L. Then when we put that into our F equals ma equation, which is mg minus t equals mx double dot, we get mg minus 4 mg x over L, and this is a more algebraic way of seeing that these two will always cancel out, as we saw in the previous examples. Final step then is just to rewrite this. The m's cancel out. X double dot we know is d2x by dt squared, and that equals 4gx over L as required in the question. When P is released, AP equals 7/4L. So at the maximum extension here, we're at 7/4L, which means from O, which is 5/4L, down to the end is 2/4L, or L/2, and that is our amplitude. The point B is a distance L vertically below A, so point B is at the natural length of the spring here, and the question is, find the speed of P at B. So as the particle comes to the natural length of the string, what is the speed? Well, we've done a little bit of work here already to find A. We know the displacement x, where we want to find the speed, is 1/4 L. So the only thing we need to find the speed now is omega, and we know omega from part B is equal to the square root of 4g over L. So that's 2 root g over L. So to find the speed at B, we can use this equation, where omega is equal to 2 root g over L, A is equal to L/2, and x at point B is equal to L/4. V squared, 4g over L, times L squared over 4 minus L squared over 16. That gives 3g L/4, so V is equal to root 3gL over 2. Part D. Describe briefly the motion of P after it has passed through B for the first time. So if it's released from rest here, passing through B for the first time is on the way up, until it next passes through O. So as it comes up here, it passes through O, maximum speed here, and then it slows down, but it is still going up at this point because the amplitude is bigger than that distance. So as it passes through B, it moves freely under gravity for a time before it comes back to B, and then it moves with simple harmonic motion again down to O. I won't write all of that out, but the two key points it's looking for is that above the point B it moves freely under gravity, and then as it comes back down B to O it moves with simple harmonic motion again. And that, I hope, is enough for you to have a go at the questions from exercise 3E, the chapter 3 review exercise, and because we're halfway through the book now, review exercise 1. And maybe I'll see you for chapter 4.